This is Lisa Allen, and today we're going to be talking about the fundamental theorem of calculus, but we're going to start off with talking about area as an accumulation function. We are going to talk about how differential calculus, taking the derivatives, is related to integration or antiderivatives. And Isaac Barrow discovered that these two operations are inverses of one another. So before we get started, just think about what you know about area being positive, area being negative, that you've learned in terms of the definite integral. So here we go. Here's the warm-up. We're going to look at area as an accumulation function, and with that, we're going to look at 5 graphs and find the area of each of the graphs, keeping in mind that when you're dealing with area, that area is positive above the x-axis and negative below the x-axis. So I'd like you to pause your video, complete your problems, and then turn it back on and check your answers with the solutions that will be given. So I'll see you back in a minute. So the areas captured turned out to be, for the first graph, 1. The second graph is 3. The third graph is 4.3. The fourth graph is then 3 again, and the fourth graph is 1.7. So if you're looking at these, you're thinking, okay, the accumulation function then from 0 all the way to the end turns out to be 1.7. So what we're doing is that we're laying the groundwork through this warm-up for notational fluency, understanding that an integral equation, g of x is equal to the integral from 0 to x of f of t dt, is the notation that we want students to get used to, and that it really just means that area is building from left to right, from 0 to x. Now take a moment, and what you did with the warm-up, I'd like you to try to convert that over to integral notation, where you're using g of x is equal to the integral from 0 to x of f of t dt, and try to find the following: g of 1, g of 2, all the way through to g of 5. When you're done, turn your video back on, pause it, turn the video back on when you're done, and check your answers. So for the previous warm-up, we have g of 1 is equal to the integral from 0 to 1 and has the value of 1. G of 2 is equal to g of 1 plus the integral from 1 to 2 and has a value of 1 plus 2, which is equal to 3. G of 3 is equal to g of 2 plus the integral from 2 to 3, which would give a value of 3 plus 1.3, or 4.3. G of 4 equals g of 3 plus the integral from 3 to 4 and has a value of 3. And g of 5 equals g of 4 plus the integral from 4 to 5 and has a value of 1.7. So now let's look at another example where f is a function whose graph is shown, and g of x is, of course, the integral of from 0 to x of f of t dt. And let's take a look at evaluating g of 0 all the way through to g of 6, g of 1, g of 2, g of 3, all the way up. So first we want to consider g of 0. So let's take a look and see what we get with that. So if you look at g of 0, you notice something. Oh, over there. You notice that from 0 to 0, there is no width. So how can there even be area if you have no width? So g of 0 is the integral from 0 to 0 of f of t dt, which is going to equal 0, nothing. So for g of 1, the integral from 0 to 1 of f of t dt looks like the value is 1/2, which is equal to the area of the triangle which lies below the curve and above the x-axis in the positive region. So the integral is equal to 1/2. G of 2 is equal to the integral from 0 to 2 of f of t dt. Therefore, the area is equal to 0 because the positive 1/2 area above the x-axis cancels with the negative 1/2 area below the x-axis. So 1/2 plus negative 1/2 is equal to 0. So the integral is equal to 0. So g of 3 accumulates another negative 1/2 to the area. So g of 3, the integral from 0 to 3 of f of t dt, is equal to negative 1/2. G of 4, the integral from 0 to 4 of f of t dt, then is equal to 0 because all the areas cancel out and the sum is 0. Your area on top of the x-axis is equivalent to that on the bottom of the x-axis, and so the sum of your integral is 0. Now moving to the right one more unit, g of 5 is equal to 3/2. The integral from 0 to 5 of f of t dt has a total net area of 3/2 or 1.5. 6 now is the integral from 0 to 6 of f of t dt, and that equals 3/2 plus 5/2, which will total to 8/2 or 4. So we're almost finished. We have one more irregular shape to estimate because we don't know the exact area of the figure, but we'll look at g of 7 next. The estimate now for g of 7 is g of 6, which is 4, plus the area from 6 to 7. So if you look at one of the integral representations that I gave you g of 7 is equal to g of 6 plus the integral from 6 to 7. And then I gave you another integral representation, which is g of 7 is equal to the integral from 0 to 7 of f of t dt. Either are valid and equivalent. So it looks like g of 6 is 4. G from 6 to 7 is another 2.25, so add them together and you get 6.25 for g of 7. So there you have it. There it is. There you go. So we have our function g of x illustrated as a graph for the accumulated area, a table of values for g of x, and an integral equation for g of x, including the g of 7 that we calculated as the completed area. What is the g of x minimum value? It appears in the table to be -1/2. What is the g of x maximum value? That appears to be 6.25. But on the next activity, I'd like you to graph the function g of x using a table of values to be able to visualize the minimum and maximum values of g of x. So that's what your graph should look like. Now, I'd like you to pause your video and I'd like you to label your extrema on the graph. Remember, extrema are your minimums and maximums, and you have two types. You have local minimums and maximums and absolute minimums and maximums. So take a moment, look at your graph, and think about the extreme value theorem and the extreme value theorem on a closed interval. Okay, so try that, pause your video, and we'll be right back. Talk about the extreme value theorem a little bit, that the extreme value theorem guarantees that if you have a continuous function on the closed interval AB, there must be an absolute max, there must be an absolute min. And in this case, you're seeing that you have a local minimum at x is equal to 3, and that local minimum value is -1/2. You have a local maximum value at x is equal to 1, and that value is 1/2. And then you have an absolute maximum value at x equal to 7, and the value is 6.25. And then you have an absolute minimum, which is also a local, at x is equal to 3, and that is -1/2. So in this way, we've been able to look at the fundamental theorem of calculus introduction as accumulation of area as the integral as an integral equation. So we'll come back for video part 2 in the next series, and we'll start to talk more about the first fundamental theorem of calculus.